In this video, we are going to start chapter 5 and we are going to speak about the first section is going to be about inverse functions. We are going to have two objectives. The first one is going to be how to determine whether a function is one-to-one, and if the function is one-to-one, we need to find the formula for this for the inverse of this function. The second objective is going to be to simplify expressions of the type f composed with f inverse of x and f inverse composed with f of x. Let's first consider the relation that given in this example. We have h equals, we have 4 points. So we need to check whether this relation is function or no. To check the relation is function or no, recall the definition of the function. The function is a relation where every element in the domain corresponds to only one element in the range. So we look at the domain elements. For example, -8 is only corresponds to 5. There is no -8. Another -8 corresponds to another element in this set. Also, the 4 is just corresponds to the -2. -7 is only corresponds to 1. 3.8 is just corresponds to 6.2. So it is a function. It is a function. And how can we see this? If you go to the GeoGebra and try to graph these points, let me try to plot these points. Okay, so the points are -8, comma, 5. The other point is 4, comma, -2. So -7, comma, 1, 3.8, 3.8, comma, 6.2. If you look at these points, these are all of the points. And if you remember to check whether this set represent a function or no, we used to do the vertical line test. The vertical line test. And if you try to do the vertical line test and see what's happening, if the vertical line test, if you just draw vertical lines, and these vertical lines passes through only one point of these points, so we are going to have a function. If the vertical line, one vertical line, passes through more than one point, then we are not going to have a function, which is the same idea of having two values from the range for one value from the domain. So this is a function by using the vertical line test. These are different points, remember. These are different points. Here is 4, and the other one is, what is the other point, is 3.8. They are not equal, remember. This x, oh, where is it? I lost it. Okay, here. This x here, where's the other point? Okay, here is the x is 4, but x here is 3.8. So we don't have these two lines, they do not appear on one line, okay, one vertical line. So let's go back. Now I would like to investigate and interchange the first and the second coordinates. I would like to interchange them, okay? So I'm going to do what? I'm going to get the 5 here, so interchange these two coordinates. Y coordinate becomes x coordinate and x coordinate becomes y coordinate. Then I'm going to get this kind of relation. This is another relation indeed. It is another relation. It's a new relation. Okay, and if I would like to check whether this guy is a function or no, again we can do so. This is the 5 corresponds to the -8. The -2 corresponds to 4. The 1 corresponds to the -7. 6.2 corresponds to 3.8. So every element of the domain, this domain here, we are talking about this guy, this set now, just corresponds to one element of the range. Don't think about this notation. We are going to speak about this later. The h to the power of -1. So let's see this kind of relation on the GeoGebra again. Okay, so this is our first relation, correct? This is our first relation, A, B, C, D. So let's go and interchange the coordinates and see what's going to happen. So the first one, we're going to have 5 comma -8, correct? The second one, let's change their colors if we can. The color is going to be like red here. Okay. The other one is going to be -2 comma 4, right? And the other one is going to be 1 -7. And the last one is going, what is this? Okay, here we go. This is my mistake. So it's going to be 1 -7. And the last one is going to be 6.2 comma 3.8. So let's change the color of these guys. So this is going to be in red. This is going to be in red. And this is going to be also in red. So the blue points represent the H set, and the red points represent the h to the power of -1. I don't like this name, but let's keep it for now, and we're gonna change it later. Okay, so because I would like to make like some connection, so to get to connect these points together, I would like to connect A with E and B with F and C with G and D with H, because we just interchange the coordinates. So I'm going to rename these guys. So I will be trying to rename this. So this E, I'm going to call it A prime, okay, A prime. And F, I'm going to call it B prime as well. G, I'm going to call it C prime. C prime. And H, I'm going to call it, guess what? D prime. That's perfect. Okay. Now let's look at this. Let's look at this. So D and D prime, B prime, A prime, and C prime. Look at the distance between these guys. And if we think about matching these points like D with D prime, B prime with B, and A with the A prime, and C with C prime, we are going to notice something. We are going to notice something. I would like to draw the line, a straight line, that this line is going to be in the middle between these 2 points. For example, what is the middle point between the D and D prime? There is a middle point, right? What is the middle point between B prime and B? There is a middle point. What is the middle point between A and A prime? You can't find it anyway. And what is the middle point between this point and this point? We can add the point, the coordinates, and divide them by 2, right? If I would like to add, for example, let me go back to my presentation. What is the middle point now between A and this is A? This is A. Let me erase this. What is the middle point between this point and this point? What is the middle point between these 2 points? What we do, the midpoint. Midpoint. We just add x's together and we divide by 2, comma, we add y's together, then we divide by 2. So -5 or -8 plus 5 is -3 divided by 2 is -3 over 2. The other one is also -3 over 2. Correct? We get the same point because you add the 2 numbers and you divide by 2. So you're going to get the same number because you just interchange them, right? So let's do the rest. So this one, -3 over 2, -3 over 2. The midpoint. So the first midpoint, let's plot this point. So you got -3 over 2. -3 over 2. This is minus here. Comma. -3 over 2. So this is the first point, and I'm going to change the color of this point to what? To the to yellow. Okay, and I'm going to call this point because it's the middle point. So I'm going to call it A small. Okay, it's going to be A small. Then let's find the rest. Let's find the middle point of B and B prime. So -2 plus 4 is 2. Divide by 2, we got 1. So we have 1, 1. So this point, I'm going to call it B. B is going to be 1, 1. Okay? So 1, 1. So what is this point? We're going to call it, as I said, B small. Okay, perfect. Now, what is next? And let's change this to yellow. Who's next? C, right? -7 plus 1, -6 over 2 is -3. So we're going to have -3, comma, -3. At this point, I'm going to change the name to C. Perfect. And I'm going to change the color to yellow. Perfect. Now, the last point, which is D now. What is D? D, we got 6.2 plus 3.8, so we got 10. 10 divided by 2 is 5. So the middle point is going to be what? 5, 5. And this is what? This is D. Change the color. We got these middle points between, A prime, B prime, and so on. Okay, the first observation is these middle points, the first coordinate is equal to the second coordinate. For example, if you look at A, what is the middle point between A and A prime is -3/2, -3/2. And the middle point of the B, the line passing or the line connecting B and B prime is the point B small, and the B small is 1, 1. So x coordinate is equal to the y coordinate. The same thing with C. C coordinate, x coordinate in the C is equal to the y coordinate in the C, -3, -3, and the last one 5, 5. So x is equal to y. So x is equal to y, right? X is equal to the y. So x is equal to y. So why don't we graph this function, linear function, when x is equal to y, right? In all points A, B, C, D, small letters, x is equal to y. So why don't we, graph this? Let's try to graph it. Y equals to x. Yeah, all of these points are on this line, Okay, so what does this line represent? It represents the mirror. It's the mirror of the points. So these points are always reflections of each other across this line, right? So the set h to the power of -1, we don't like this name because it's not h to the power of -1. We're gonna call it h inverse. So we have two sets, h and h inverse. And we have noticed that h inverse is just nothing. It's just a reflection of the h across this line. Y is equal to x. Because again, if we just look at the reflection here, this point is a reflection of this point here across this line, right? This point is a reflection of this point across this line. Is the mirror, right? The mirroring line. A is the same thing, and C is the same thing. So h is a relation, and h to the power of -1 or h inverse, we cannot say, we don't say h to the power of -1. Nothing to do with the power. It's just a symbolic name. So we call it h inverse is the inverse relation of the h, okay? So how did we get the inverse relation? We just interchange x and y coordinates. And what is the relation between the relation itself and its inverse? The inverse of the relation, it's always what? Is always a reflection of the relation itself across the y equals x. Y equals x. So let's get back. Let's get back. Good. So when we go from the output of the function back to the input or inputs, we get the inverse relation. The inverse relation. And there is a good example, and we use actually a lot, which is when we convert from the Fahrenheit to Celsius. These two functions, the first one is a linear function, okay, and the second one is a linear function as well. So are these guys inverses to each other or no? So let's go to GeoGebra and try to graph these guys. Again, to know that whether this one is inverse of this one, we need to see the reflection. One of them is going to be the reflection of the other one across y equals x. Across y equals x. So now I'm going to go to GeoGebra and graph these two functions, but I'm going to do something. I'm going to call this guy y, and this guy is going to be x. The same thing here, I'm going to call this one y, and I'm going to call this one x, okay? Then I'm going to graph these two things there in the GeoGebra. So let's try to do this. So I'm going to keep the y equals x, which is um, the mirror, right? The mirror. And I'm going to hide all of the other points. So the first one is going to be y is equal to 9 divided by 5 times x plus 32. So we got the first line. Now the second line, I'm going to say y is equal to 5 divided by 9 times, again, parentheses, x minus 32. Enter. So let's go there. Okay, now we have 3 lines. The first one I'm going to change the color because I want to see something else. So this is red. One of them represents the Fahrenheit. So the Fahrenheit degrees is a subject to the formula. So Fahrenheit is written in terms of the Celsius degrees, and the other one, the Celsius, is written as a function of Fahrenheit degrees. So these 2 lines, look at them, and look at the middle line. It is a mirror. How did I know? Any point, take any point on the blue one and go straight to the other side. You're gonna see that reflection of this point. So this point, if you go to the other side, you're gonna see the mirror. It's a reflection. The reflection of this point is on the other hand. It's on the other side. Take any point and go straight line. You're gonna find it on the other hand, on the other side. So this is example of how we see the functions and their inverses. Okay, y in the first example I said f is y, c is x. Then I said c is y and f is x because this is the way that we are going to find the inverse of the function. So let's go and try to do more examples. So to sum up things, the first idea. So when we interchange the first and the second coordinates of each ordered pair of the relation, we get the inverse relation. Example. Consider the relation G given by this G. Graph the relation and find the inverse and degraph it. We did already this for the first example, so this is your task to do. Get the inverse and graph the relation. You can't find the solution here as we did already in the previous example. Find the equation of the inverse of this relation. So how to find the equation of the inverse of the relation? As we did in the points, what did we do in the points? When we have, ordered pairs, we interchange x and y, right? We are going to do the same thing. I'm going to interchange. So interchange what? The variables. To produce the inverse relation. So how do I interchange? Just easily interchange. Just y is going to be x. X is going to be y. This is a squared. And again, x is going to be y. So this is the inverse relation. So this is the inverse relation. Do you want me to graph them? Yes, we are going to graph them. Let's go. What do we expect? We expect that what we are going to have, so we are going to have the relation and its inverse are always what? Reflection of each other across the line y equals x, right? So let's graph. So again, I'm going to hide these guys and I'm going to keep y equals x. So the first one is y equals x squared minus 5 times x. So this is the first relation. The second relation is going to be x is equal to y squared minus 5y. Correct? Enter. So again, let's go and see what's happening. Before going there, let me just change the color. So this is going to be dark blue, and this is going to be, I don't know, this is going to be so many pretty colors here. So this might, no, I don't like it. Okay, green. Yeah, green tells the story. Okay, let me go there and see what's happening. So we have the first one is the blue, and its inverse is the green, or the other way around. So are these guys really inverses to each other or no? Take any point on the blue one, and look at its inverse. Is it on the other hand of that mirror, which is y equals to x? Yes, it is. For example, take the easy point, the origin. The origin, 0, 0. It just says 0, 0, right? Take another point. Take another point. For example, if you take, let's take that point that we can read, easy point. For example, this point. This is, I guess, 0, 0, 5, right? This is 0, 5. Or 5, 0, sorry. This is 5, 0. So we're expecting to see the other point on the other graph, which is going to be 5, 0. 0, 5. So this is 5, 0. The other point is going to be on the other graph is going to be 0, 5. So it is 0, 5 there? Yes, it is here. On the other hand, look. Match these 2 points. This point has a mirror point, which is, or a reflection point, which is on the other side of this graph, the red one, and so on. So this is the beauty of the inverses of the relations. So let's get back. Okay, and we can see them here, and you can look at the some points. If you take some points, actually, if you take some points, so look at these. For example, this is y, and this is the x. If you change them, just change them. Let these guys to be for x and the other ones to be for y, and graph the functions or the relations. Sorry, you're gonna get the inverse of this relation. Let's look at something now. The graph, the relation y equals x squared minus 5x, this one, in blue. This relation is a function, correct? Why it's a function? Because we know it's a function. It's a quadratic function, and we studied this already before. And if you perform the vertical line test, you're going to find that this is a function. This relation is a function. Why? Because just take vertical lines, straight lines, vertical lines. Every vertical line is passing the parabola only in one point, the blue parabola. We are talking about the blue parabola. The vertical lines, they passes the blue parabola in only one point, each of them, not more than 1 point. So that's why the quadratic relation here is a function. Yeah, but the inverse, look at the inverse now. The inverse relation, is it a function or no? Who can tell me? Yes, correct. It's not a function. Because if you take a vertical line, just one vertical line here is enough, because one vertical line passes through 2 points. points. So the inverse of this relation is not a function. So the inverse is not a function. So when the relation is a function, is it always its inverse is going to be a function? No. This is the next point that we are going to talk about, and this is kind of an introduction. So in this example, we have shown that we have a function, but its inverse is not a function. If you remember the first example we gave at the beginning, both of them were functions, the relation and the inverse of that relation. But now, the other one is not a function. The inverse is not a function. Okay, so when we are going to have the inverse is also a function, when the relation itself is a function, there is another concept, which is having one-to-one functions. What does it mean by one-to-one function? Do you have a one-to-one function? This relation in the blue, is it one-to-one function? The relation in the blue is a function. Now this is a function. I'm talking about the blue curve. The blue curve. Is it one-to-one or no? Let's think about it. I'm going to take it to the GeoGebra and see. Okay? So again, let me do what? So let me take this graph. Y equals, oh, we have it already. So we have it here. So let me just hide these guys. I'm going to keep the blue line. Okay, this is the one that we had already there. Okay, so this one is a function because it passes the vertical line tests, right? But is it one-to-one function or no? What does it mean by one-to-one function? One-to-one function means, let's look at this point, which is what? This is 5, 0. Why I do keep taking this point? Because it's easy for me, okay? Because it's an easy point, okay? And this point actually is easy. This is 6, 7. This is 6, I guess. This is 6, yes. It is 6, 5. This is perfect. I'm taking 2 points. Anyway, so the first point, 5, 0. And this point, the other part, what is this? This is 0, 0. What about this point? This is negative 1, 5. What is the common thing among these 2 points? What is the common thing about these 2 points? Do you notice that they have the same y value? Negative 1, 5, 6, 5. X is different, but y is the same. It means that we have two x values, two x coordinates, negative 1 and 6, and they correspond to 5. They correspond to the 5. The same thing with the 0. So the 0 in the domain, in the range, we have 0 in the range and 2 elements in the domain. So the 0 and the 5 in x, they correspond to the 0 and the y. So what does this mean? This means that this function is not one-to-one. Is not one-to-one. It's from its name, one-to-one. 1 from the x coordinate has to match with only one element from the range, and it has to be unique. And the element in the range has to have only one input for it. It has to have one input. I mean, this element in the range, it's supposed to be matched with one element from the domain, not two elements from the domain. So this is the meaning of one-to-one function. And this is not one-to-one function because the 5, we can give one example. The 5 in the range is matched by -1 and 6. So these two elements in the domain, they took one element in the range. So this is not a one-to-one function. How do we test this? These 2 points are on the same vertical line. If you look at them, -1, 5, 6, 5. So the horizontal line. So the horizontal line test tells you whether the function is one-to-one or no. So now we have 2 tests. The vertical line test that we spoke about earlier tells you whether the relation is a function. We are done. But now we need to go further. This function, is it one-to-one or no? To do this, we perform the horizontal line test, and we check. If the horizontal line passes through more than 1 point, then the function is not one-to-one. Otherwise, it's going to be one-to-one. But in this case, just take one of them. One horizontal line is enough. If one horizontal line passes through the function, or the function in more than 1 point, it's not one-to-one, period. Then what? Why do we care about one-to-one and not one-to-one? Oh yeah, because here, if you remember, if you go back, let's go back. Yeah, because this function is not one-to-one, its inverse was not a function at all. So the blue function is a function. Is it one-to-one? No, not one-to-one. So we got the blue function, the blue. The blue line is a function. The blue line is a function. Is a function. Is it one-to-one? But it's not one-to-one. It's not one-to-one. Thus, its inverse is not a function at all. Is not a function. Yes, we found the inverse. We found it, but it's not a function. So I'm going to take the second definition. F of A is equal to F of B, then A is equal to B. In our example, what did we show? We show that F of 0 is equal to F of 5. If you go back to the points, then because here f of 0 is what? Is 0, and f of 5 is 0. Then 0 is equal to 5, but this is incorrect. So that's why this is not one function. Again, if A is not equal to the B, if you remember, where is it? Let me take these two points. I'm going to take these 2 points, okay? I'm going to take these 2 points, -1, 5, 6, 5. So -1, 5 and 6, 5. So these 2 points are on the function, okay? I took these 2 points. You can take other corresponding points. Any 2 points are on the horizontal line, okay? On the graph, and they pass through the horizontal line. So what I'm going to do, I'm going to check now. I'm going to check what is f of -1. F of -1 is 5. What is f of 6? F of 6 also is 5, right? So what can I conclude? I conclude that f of -1 is equal to the f of 6, correct? They are equal because each of them equals to 5. However, the numbers inside, the inputs are different. The inputs are different. So this is not equal to this. -1 is not equal to 6. So this is not to one function. This is not one-to-one function. One-to-one function, if the images are equal, this is the summary. If the images are equals, then the domain values have to be equals, okay? If the images are equals, if the outputs are equals, the inputs have to be equals. In this case, this is not happening, okay? This is not happening. We found that we have equal images, but the inputs are not equals. So that's why that function is not one-to-one. Now, determine the following functions. These are one-to-one or no. Let's look at the first one. We have 1, 3, 2, 4, -1, 9, 0.5, negative. Is it one-to-one or no? We just look at the range. The range 3 corresponds only to the 1. The 4 corresponds to the 2. The 9 corresponds to the -1. -1 corresponds to the 0.5. So every element in the range only maps to one element in the domain. So we are good. So this is one-to-one. Here, 3 maps to the 1. Also 3 maps to the -7.5. So the 3 maps to 2 elements. So this is not one-to-one. So f of 1 is equal to 3. And f of -0.7 is also equal to 3. And these two guys are equal. So f of 1 is equal to the f of -7.5. The images are equal. However, the inputs are not equal, but 1 is not equal to the -7.5. So this is not one-to-one. Not one-to-one. Okay? Not one-to-one. Or you can just tell me that the 3 in the outputs corresponds to 2 elements in the domain. So it's not one-to-one function. Y is equal to the x squared minus 4. We know what is this, and we did something similar right now. This is a quadratic function, and if we graph it, it's parabola, right? And it's shifted down by 4. So it's going to be something like this. Is it one-to-one? No, because it failed the horizontal line test. The horizontal line passes through 2 points. It's not one-to-one. So the inverse is not an exponent, as I said. So we call it f inverse, and it doesn't mean this. This is wrong, okay? It's just a symbolic. It's just a symbolic name. So we call it f inverse. We read it f inverse. F inverse is when we're talking about the function, the inverse of the function. Okay, now let's summarize what did we cover in the last point. If the function f is one-to-one, then the inverse is a function. If the domain of the one-to-one function, f is the range of the inverse. So the domain of the one-to-one function is the range of the inverse. And the range of the one-to-one function is the domain of the inverse. Okay? The last one is the function is increasing over the domain or decreasing over the domain is always one-to-one function. If you have a function that is increasing all the time, so it is one-to-one because it passes the what? The horizontal line test. Okay? So this function, for example, is one-to-one because it passes the horizontal line test. Okay? Okay. So from this, who can tell me which one is the one-to-one? Okay, and if the function is one-to-one, then it's going to have to, then its inverse is going to be a function, right? So look at the horizontal line here. The horizontal line, so no horizontal line passes or intersects the line, the line or the function more than once. More than once. So what is this? Thus, the function is one-to-one, and the inverse, consequently, the inverse is a function. This is for A. For B, look at the horizontal line test. You find that the horizontal line passes through 2 points. So what can we say? We say the horizontal lines for B now. The horizontal line intersects the graph of the function in more than once. Consequently, what can we say? So the function f is not a one-to-one. Okay, so what is the conclusion? Then, thus, the inverse is not a function. Okay, is not a function. What about C? C, the horizontal line test passes through this graph of the function only in one point, all of them. Take any horizontal line. So this is what? This is a one-to-one function. So it's a one-to-one function, and because it's one-to-one function, the inverse is going to be what? A function. The last one, the horizontal line passes through the graph of the function in more than one point. So this is not one-to-one function. Therefore, the inverse of this function is not going to be a function. Okay, next, how to obtain the formula for the inverse. I give you a function, then I'm asking you to find the inverse of this function. First of all, you replace f of x with y. First step. Then we interchange x and y. Then we solve the function for y. At the end, you replace y with f inverse. So this is the inverse function. So we have only 4 steps. So replace f with y, interchange x and y, solve for y, then replace y with f inverse of x. So here we go. The first example here. F of x is a function. F of x is equal to 2x minus 3 is one-to-one function. Or we need to determine, is it one-to-one function or no? We have to determine whether this guy is one-to-one function or no, right? So what you have to do is to graph it. We graph this one and check whether it passes the horizontal line test or no. So let's go and graph it. 2x minus 3, or you can use GeoGebra, or you can use set of points in a table and graph it. Okay. If you want to do it quickly, you can pick some x values and find f of x. Check, for example, -1, 0, 1, because it's a straight line. It's a linear function. So plug in -1 in the function, you get -5. Plug 0, you get -3. Plug 1, you get -1. Then you graph this. So -1 corresponds to the -5 here, then 0, -3 here, then 1 to the -1 here. 1, -1 here, something here. So this is the straight line, almost something like this. So this is what? This is straight line and it passes the horizontal line test. So it is 1-to-1. So what can we say? Or use GeoGebra. Okay. So the graph of the function f passes the horizontal line test. Thus, it is 1-to-1. And consequently, and its inverse is a function. So this is the first idea. Okay. So how to find it? How to find the inverse? Step number 1. How to find the inverse? I'm going to replace f of x with y. So here's the function. So we got y is equal to 2x minus 3. Step number 2, interchange y with x, okay, or x and y, or y and x, whatever, x and y. So how to interchange this? So what do we get? Now we have y equals to 2x minus 3, so we are going to have x equals 2y minus 3, okay? Then next step, step 3, solve for y. So we got what we have now. We have x equals 2y minus 3. How to solve for y? Just as we do with x, as we solve with, for x. So I'm going to add 3 to both sides. Add 3 to both sides. What do we get? We get 2y is equal to the x plus 3. Then we divide everything by 2, all of the terms by 2, or you divide both sides by 2. Either some students got confused about this. I'm going to do it in two ways. Either I'm going to divide every single term in the equation by 2, then I'm going to get y equals x over 2 plus 3 over 2, or if you divide both sides by 2, you're gonna get x plus 3 over 2, and these two quantities are the same. Okay. Step number 4. Now I'm going to replace y with f inverse, because it is a function. Then I can confidently change y with f symbolic f inverse of x, with a simple f inverse. So f inverse of x is equal to what? X plus 3 over 2. So this is the inverse of the function. And if you would like to check whether this is really the inverse, you can create another table. Okay, create another two tables and see. You can compare them, or you can graph them. If you graph this one, If you graph this one, y equals to the x plus 3 over 2, and the graph the original one, you're gonna find that these two graphs are what? Are kind of reflections to each other across the y equals x. Okay, so let's see them. So these are two lines, and these are reflections to each other across y equals x, correct? So the first one is the function, the other one is the inverse of that function. Okay, the second point that we are going to talk about is the inverse functions and the composition. If the function f is one-to-one, so now this is a condition, this is a very important to have a one-to-one function. Because if the function is one-to-one, then the inverse is going to be a function. Now, the inverse is not only a function, the inverse is going to be unique for this function. So every one-to-one function has only one inverse, And how do we check whether the inverse function is really an inverse to that function or no? We are going to do two things. We are going to use the composition function. The composition, we are going to use the composition. So f inverse composed with f of x, if it's equal to x, and f composed to the f inverse of x is equal to x, then if we get this, if we did the composition between f and f inverse in both ways, and we got the answer was x, the answer has to be x, then these two functions are inverses to each other. Okay, these two functions are what? Inverses to each other. If this is failed, then this inverse is not an inverse to that function. Okay, example. So we are going to use the composition functions to show that the inverse is equal to x minus 8 over 5 for this function f. So the question is, f inverse, is it really an inverse to that function f or no? So I'm going to check f composed with f inverse. First, I'm expecting to get x, the answer, the final answer. And we are going to do what? F inverse composed with f, and also I'm expecting to get x at the end. If I get x at the end in both ways, that means that f inverse is really the inverse of this function. Okay, so how to do this? So f composed, if you remember, f composed with f inverse is going to be f inverse of x. This is the first step. So the input for the function f is going to be the f inverse of x. So this is equal to what? Then I'm going to take this off and replace this by what? Its formula. So f inverse of x is what? So we have f is already there. And what comes inside? It comes x minus 8 over f. Okay? So look at this. This is f inverse. Okay? Then next step is going to be what? I'm going to find the value of the function. Now we are in f. What is the domain in f? It's x minus 8 over 5. Then I'm going to plug this. I'm going to plug this into the function f. Okay? So it's going to be what? It's going to be 5 times x. The input. What is the input? The input is what is highlighted in yellow. So it's going to be x minus 8 over 5 plus 8 equals. Now, what we get 5 times this parentheses over 5, correct? Plus 8. 5 cancels with 5. Then what we get x minus 8 plus 8. And this is equal to what? It's equal to x. Perfect. And this is what we are expecting. So did we get this? Yes. Now the other way around. So f inverse composed with f of x. So my domain for the inverse is going to be f of x equals f inverse. Now we check this. Is it correct or no? We check this guy. So f inverse. Now I'm going to plug the f of x formula in the domain of the f inverse. So I'm going to take this off and put what? 5x plus 8. Now, what is the domain of the inverse? The domain of the inverse is 5x plus 8. So let's calculate this and plug this into the inverse. So what I'm gonna get, this is the inverse. Remember, this is the inverse. And this is the function. Okay? So this is equal. Plug 5x plus 8 into the f inverse. What do we get? We get, this is 5x plus 8, okay, minus 8 divided by 5. How does this happen? Because I plug in this into the inverse. This is the inverse. This is the inverse. Okay. So what do we get? 8 minus 8 is 0. Then we get 5x over 5, which is an x. So we got x. F composed with f inverse of x, we got x. And f inverse composed with f of x, we got also an x. So what can we conclude? We conclude that f inverse is an inverse, is the inverse of f of x. And f inverse is equal to this. It's correct. It's correct. It is the inverse and it's equal to this. Okay. So the question says, show that the f inverse is equal to x minus 8 over 5. Then we show that it is the inverse and it's equal to x minus 8 over 5. Okay, when the inverse of the function is not a function, the domain of the function can be restricted to allow the inverse to be a function. So sometimes the function is not one-to-one, like this. This function is not one-to-one. And the domain is from negative infinity to infinity. Correct? So how to do with this function? And because this function is not one-to-one, the inverse of this function is not a function at all. If I'm thinking to have an inverse function of this function, I cannot. Right now I cannot. So what we need to do is maybe to erase part of the function, to restrict the domain. Maybe instead of having the domain from negative infinity to infinity, we can start having the domain from 0 to infinity. So having the right hand side of this function. If you look at now the right hand side of the function, it is one-to-one. Okay, without the left hand side of the function. Or you can take the left hand side of the function from negative infinity to 0. So sometimes in some applications we need to restrict the domain. Restricting the domain helps you to create or to find an inverse function of the function. Okay, in this example, we are given f of x equals x squared minus 2. And we know this is parabola translated down by 2 units, and it's not one-to-one function. So determine whether f is one-to-one. No, it's not one-to-one because it fails the horizontal line test. It fails the horizontal line test. So it's not horizontal. No, it's not horizontal. It's not one-to-one. No, it's not. It's not one-to-one. Why? Because it fails horizontal line test. Horizontal line test. How it fails horizontal line test? By passing through the graph in more than once. Is the inverse of f a function? No, it's not. No, it's not a function. It's not a function. Why it's not a function? Because f is not one-to-one. Find the formula for the inverse of f. Can we find the formula of the this function? Let's find a formula. So f of x is equal to what? X squared minus 2. So f, we're going to replace it with y. So we're going to have y equals x squared minus 2. Then I'm going to interchange x and y. Then I'm going to have x equals y squared minus 2. Last step, I'm going to solve for y. Solve for y, we're going to get y squared equals x plus 2. Then take square root to both sides, you get y equals positive and negative square root to the x minus 2. So what did we have? We have two portions. Okay? So that's why this is not a function. This is not a function. It's an equation only. It's an equation. For example, if the input was 2, this is plus. For example, so it's clear that this is not a function. And this is the inverse relation now. The inverse relation, it's not a function. Why it's not a function? For example, take, let x be 2. Let x be 2. What do you get? You get y equals plus or minus 2 plus 2 is 4. So what did we get? Plus or minus 2. So when x is 2, y is going to be 2 or y is going to be negative 2. So this is not a function because the domain, one value in the domain maps to two values in the range. So it's not a function. Good. So restrict the domain of f in order to allow the inverse to be a function. Now we are going to restrict the domain. How we are going to restrict the domain? From the graph of the function, you can do what? As I said, you can just pick the domain to be, you can just choose this is the function. You can choose only the right part, the right hand side part, and ignore the left hand side part. So I don't want this to be part of the domain because now the domain of f is from where? Negative infinity to infinity. And this is a polynomial, we know this. I can restrict, so choose what? Choose a new domain of f to be from where to where? From 0 to infinity. If you choose new domain from 0 to infinity, you guarantee that f is going to be, so f of x, which is x squared minus 2 on from 0 to infinity, so this is the domain, is 1-to-1. From 0 to infinity, because the left hand side is not going to be there. Someone is going to ask, why didn't you choose from negative infinity to 0? We don't care. The question says just restrict the domain. Just do any restriction, okay? Restrict the domain. So this is what I'm going to do. I'm going just to choose this part. Of x is equal to x squared minus 2, and we restricted the domain from 0 to infinity, and we can even take the 0. We can take the 0, closed interval. We can consider the 0. So x is positive values only. Take x to be a positive value. So this is 1 to 1. Then how to find the inverse? We're going to follow the same steps. So here x in the domain, look, x is going to be greater than or equal to 0. So the domain of the function is positive. And if you remember, we said the domain of the function, okay, the domain of f of x of the function is the range of f inverse of the inverse of its inverse of its inverse. So what do I mean? Let's find the inverse the way that we learned. So the first step of finding the inverse again, just replace f of x with y. Then step number 2, interchange x and y. Then number 3, solve for y. You get y squared equals x plus 2. Then square root to both sides. You get y equals square root of x plus 2. So when we take square root, usually we get positive and negative, right? Positive and negative. But hold on. Let's look at this. The domain of the function is the range of its inverse. So because the domain is x greater than or equal to 0, so y is going to be greater than or equal to 0. So because here we have positive and negative, we cannot take both of them. We only take one of them. So I'm going to erase the negative because this gives you y is going to be greater than or 0. Okay? So this is my inverse. Y equals square root of x plus 2. And it's f inverse. Then last step, replace y with f inverse. And y is greater than or equal to 0. And this is everything for today. And the last idea I'm going to summarize. Sometimes you have relation. The relation can be a function and can be not a function. It could be not a function. Now we care about the other case, when the relation is a function. When the function is 1 to 1, the inverse is a function. The inverse is a function. When the function is not 1 to 1, the inverse is not a function. What can we do when the function is not 1 to 1? We restrict the domain. Restrict the domain. When we restrict the domain, what we get? We can produce what? An inverse. There is an inverse to this function. Restrict the domain, then f of x is going to be 1 to 1. After that, we can find an inverse to this function, and the inverse is going to be a function.